Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 16, Multiplexers and Demultiplexers for the course Digital Logic Design. We are in chapter 4, and the title of this chapter, Design with Standard Modules. The next slide is a disclaimer for you to read. I cite 3 references for digital logic design, but there are many more on the internet or in your bookstore or in your local library. Chapter 4 contents, we started with decoders, decoder expansion, design with decoders, code converters, and then we talked about encoders. Today we'll talk about multiplexers and multiplexer expansion and demultiplexers. What's the multiplexer? A multiplexer is also called a data selector. Is basically a digital switch that connects one out of n data input lines to a single output line. Generally, a multiplexer has n data input lines D0 to Dn-1, one output line F, and k select input lines S0, S1 to Sk-1, where k is log to the power 2 of n. The S lines also called select lines or control lines. The k-bit select number ranging from 0 to 2 to the power k minus 1, and when this number has the value I, di is connected to the output as shown. So for instance, if we have here all ones, we will select dn minus 1. If all zeros, we will select d zeros, and f will be equal to d zeros. So we have n data line where n is equals to the power k, and we have k select line from S0 to Sk-1. Now let's design actually a 4-to-1 multiplexer. A block diagram for 4-to-1 multiplexer is shown here. We have 4 data line. Those are the input line to the 4-to-1 multiplexer. We have one output line, which is F. And we have 2 select lines because 2 to the power 2 is 4, which is the data lines. So the select line will be S0 and S1, where S1 is the most significant bit. So the data line D0, D1, D2, and D3, and 2 input select S0 and S1. The truth table is shown here. If I have S0, S1, 0, 0, I will select D0. With 0, 1, I will select D1. With 1, 0, I will select D2. With 1, 1, I will select D0. So simply from the truth table, the value of the function f could be defined as the minterm 0, D0, minterm 1, D1, minterm 2, D2, minterm 3, D3. Or simply it's S1, 0, S0, S1 prime, S0 prime, S1 times D0, S1 prime, S0 times D1, or S1, S0 prime D2, or S1, S0 D3. And the implementation of the circuit is quite simple. You see it here, and the corresponding data line. So we can generate this circuit easily, and we implement it. Just we need here the 4 input OR gate because we have 4 product terms here. And this is a sum of product formula which could be implemented easily with any types of gate, especially we can implement it with or NAND gate if we want to. How about if we like to design an n-to-1 multiplexer? Well, the general formula for F is this. So we have n input data line, we have one output, and we have log to the power 2n input select line. So once I know the select line, the data line, F will be MIDI, which is M0 D0, the first data line, M1 D1, plus Mn-1 Dn-1, where Mi is the midterm, the k input select variables, and Di is the corresponding data input. So it's really a generalization to the previous design, to the 4-to-1 MUX. Just we can extend it to n-to-1 multiplexer. There are many standard multiplexers available in the market. Mainly, we have 74151A is 8-to-1 multiplexer, and the 74150 is 16-to-1 multiplexer. 74153 is a dual 4-to-1 multiplexer. Dual, it means we have two multiplexers on one chip. Okay, controlled by the same select line and may have application for multi-bit transmission over a single bus. All of them do. On the other hand, the 74157 is a 4-bit 2-input multiplexer module which connects one of the two 4-bit inputs to the 4-bit output as selected by a select input signal. So those actually standard multiplexers available on the market. What are the applications of a multiplexer? Multiplexer have many applications. They can be used to implement the switching functions and combinational network. This will be in the next lecture. We will talk about design with multiplexers. They may be used to connect one out of n terminals to the computer input or to connect one out of n computers to one printer. So allow you to perform parallel connections, parallel to serial connections, so we can serve all the computers on one printer if we don't have one printer for each computer. Multiplexers are widely used in digital communication to transmit n channels on the single frame of data, single line of data. How to expand a multiplexer? A multiplexer, like decoders, can be expanded in a tree-like network, where the node of the tree is the output function f, and the leaves of the tree are the input data lines. The input select lines bits are divided into all levels of the network, where the most significant bits are used for node 1, down to the least significant bits for the leaf side of the tree, which is level n. As shown in this example, we would like to design a 16-to-1 multiplexer using 4-to-1 multiplexer. So here we need 5 4-to-1 multiplexers to do the job. One for the node level, level 1, and 4 to serve all the data lines from D0 to D16. And we need 5, we said, 1 for the node, and now the select lines S3 and S2 will be at the node. Those are the most significant bits, while the least significant bit, S1 and S0, will be at the leaves of the tree, okay, as shown. So we have S0, S1. So if we have S0 and S1, let's take an example, the select line 1, 1, 1, 1, starting with the most significant bit. So the S0, S1, 1, 1, we will select, actually, in each one of them, we will select the upper data line, which is here D3, D7, D11, and D15. So those will be selected. Since this is 1, 1, we'll select D15. So F will be equal to D15. F will take the data from D15, or the switch will be open to D15. Okay? As simple as this, and you can assume any other example, and you will find F will be corresponding to that example. Let's talk about demultiplexers. A demultiplexer, also called a data distributor, is a digital circuit that receives data on a single line and transmits the data on 1 out of 2 to the power k possible output line, where k is the select number of select line. So if the number of the select line is 3, we can transmit the data on 2 to the power 3, which is 8 data lines. So this is really the opposite for the multiplexer and serve a communication channel very well. So a multiplexer will transmit the data on one line. Once you receive the data on the destination side, okay, on the receiving side, you will basically demultiplex it back to the parallel data as was transmitted. So the opposite. Therefore, a multiplexer is really the inverse circuit of the multiplexer. Let's try to design a multiplexer. So designing a 1 to 4 demultiplexer, I do apologize, designing a demultiplexer. The design of a demultiplexer is identical to that of a decoder with an enable input, where the enable input acts as the data input line to the demultiplexer. So 2x4 decoder with active low outputs and active low enable input. So the active low, it means I have a valid data when the data bit is 0. And 1 is not valid data, or it is something between. You could have something between. So the data, if the data f is 0 and the select line 0, 0, this will enable me to put the 0 on data line D0. See, it is 0. When I have 0, 1, I will put the data on line D1, which is the 0 bit right here. When I have 1, 0, it will be on line D2, and the other lines will be 1s. Okay? When I have 1, 1, the F0 will be placed on D3. Okay? And when I have 1, S1 and S2, they don't care. Please correct this. S1, this is S2, not S0. We are using S1 and S2. So this is will be all ones data, which is, since the data is active low, so this is inactive data. Okay, so you'll get all ones. And so by this, you can transmit the data accordingly based on the select line to any data line. So if you control F by a specific clock to transmit specific rate, so you can transmit the data accordingly to those. And S1 and S2 can come from a counter, from a counter where this counter will transmit the data in sequence, and the data will be transferred to D0, D1. So the incoming data is synchronized by a counter, and you can put the data on the data lines. I would like to thank you so much. This is the end of this lecture. We talked about multiplexers and demultiplexers. Please subscribe, and hopefully to see you soon. Thank you, Dr. Hassan.